Hey guys, welcome back for another chemistry lesson. This lesson is going to be on thermodynamics, energy exchange, and heat transfer. So the first law of thermodynamics is the law of conservation of energy. First, we need to know what thermodynamics is. It's the study of energy and its interconversions, so between types of energy. The first law of thermodynamics is the law of conservation of energy, which means that the amount of energy in the universe is constant. So even if this thing over here loses energy, it doesn't get destroyed, it just gets transferred or changed to some other kind of energy. So you can never design a system that continues to produce energy without some source of energy, right? The amount of energy in the universe is constant. So a conservation of energy means that the sum of the energy changes in the system and in the surroundings have to equal out to be zero. Them's the rules. And so we can write this in an equation format. Here you see the change in energy. So delta is this is the Greek letter delta. It's not a triangle, but it is the symbol that means change. So just final minus initial, right? So the total change in energy of the universe is zero. So the amount of change of energy in the system has to be equal and opposite to the amount of change in energy of the surroundings in order for this to be true. So here we see there are 1, 2, 3 chunks of total energy, right? So 1, 2, 3. Before the energy transfer, our system has 2 of them, and our surroundings have 1. After the energy transfer, the system has 1, and the surroundings have 2. So my total is still 3, right? This is overly simplified, but hopefully this demonstrates to you that our total amount is the same, it just transfers or becomes a different type. So the internal energy is the sum of the kinetic and potential energies of all particles that compose a system. So the change in the internal energy of a system depends only on the amount of energy in the system at the beginning and at the end. So you will notice that on the previous slide, I said initial and final. This stays true here. Because of the initial and final business, we call this a state function. A state function is a mathematical function whose result depend only on the final and initial conditions, and how we got there doesn't actually matter. So we can write it in a formula like this. And for chemistry, what that means is the total energy change in our reaction is equal to products and reactants, final minus initial. Right? So state functions are like climbing a mountain, okay? There are 2 ways that we can climb the mountain. We can either go straight up, which is super, super steep, or we can do the whole switchbacks, windy business, right? This path is 12 miles long. This path is 5 miles long. Regardless of which trail you choose, we start here at 0 feet above sea level and end up here at 10,000 feet above sea level, we'll say. So the distance from the base to the peak is a state function, right? How far above the base you are, that idea does not care about did I take the switchbacks or did I take the direct route, right? That's a state function. I ended up 10,000 feet above. I started at 0. So the change in elevation was 10,000 feet. Now, your legs will not be a state function and will probably feel one of these more than the other. But the total elevation change is a state function. We don't care how we got there. So, in a chemical reaction, you're going to have energy flow, right? So, in this particular reaction here, we are reacting solid carbon and oxygen gas to get CO2 gas, which is the product. The total amount of internal energy in 1 mole of carbon and 1 mole of O2 is greater than, as you can see here, this the y-axis demonstrates our energy here, is greater than the internal energy in 1 mole of CO2 at the same temperature and pressure. So when we have this reaction that's happening, we have a net release of energy into the surroundings, because this energy, this change in energy, it has to go somewhere. So our system loses the energy, which means that our surroundings has to gain the energy. Right? In the reverse reaction, if I'm breaking down CO2 and getting carbon and oxygen out of that, we would have to absorb that same amount of energy. So here, the initial situation that we discussed, we lost energy, which meant that our delta E, our change in energy, was going to be negative, right? If we flip the equation around, it's going to be positive. Same amount, just a different sign to show the direction of energy flow. So when energy flows out of a system, it all has to flow into the surroundings, right? So out of our system, our reaction, into the surroundings. If we are losing energy and releasing it, our delta E is negative. If we are gaining energy or absorbing it, then our delta E is positive, which is the situation here. Right? So when energy flows out of a system, then our delta E for our system is negative. When energy flows into the surroundings, our delta E for the surroundings is positive. Therefore, our negative delta E of our system is equal to positive delta E of the surroundings. So if we flip this around and we have energy flowing into the system, whatever we are adding energy to, which in this case is our system, has the positive delta E, and the thing that is losing the energy is going to have a negative delta E. So energy is flowing from the surroundings to the system. When energy flows into the system, our delta E for our system is positive. And when it flows out of the surroundings, the delta E for the surroundings are negative. Therefore, we can write it like this. Delta E of our system is equal to negative delta E of our surroundings. All right, so what I've been showing you here are energy diagrams, which are, I'm going to call them graphical. They're visual ways of showing you the direction that energy is flowing during a process, right? So if the reactants have a lower internal energy than the products, the change in energy will be positive. If it's the other way around and the reactants have higher internal energy than the products, then the change is going to be negative. All right, we can also think about energy exchange in terms of work. And work is typically more of a physics thing that we don't talk about as much in chemistry, but we'll talk about it here. Heat and work combine together to give us our total amount of energy, right? So Q and W, heat and work, are not state functions. Their value totally depends on the process. How did we get here? Okay? So when our system gains thermal energy, that means that work is done on the system. Energy is flowing into the system. If the system is losing thermal energy, that means that the system itself is doing the work. So that gives us a flow of energy out of the system. And that's it.